In this video, we're going to be talking about the ideals of a Lie algebra. In particular, we're going to look at the definition of an ideal, and then we're going to look at related algebraic constructions. The reason we look at ideals is because understanding the ideals of a Lie algebra gives great insight into the structure and properties of that Lie algebra, and this is particularly true in the case of semi-simple Lie algebras. And just as to make an analogy, ideals play a similar role to normal subgroups. So the ideals of a Lie algebra are kind of similar to the normal subgroups of a group, if for those familiar with group theory. So that being said, let's start off with a simple notion. So we have something called a bracket of two subalgebras, which we denote using the same bracket of our Lie algebra. So the bracket big K1 bracket with big K2 of two subalgebras big K1 comma big K2 of Lie algebra L is the subspace defined to be the span of all commutators little k1 bracket with little k2 for all little k1 and big K1 and little k2 and big K2. And so it's really straightforward. Okay, so we're just going to have some Lie algebra L, and then we're going to have our two subalgebras K1, K2, and all we're saying is take some little k1 in here, some little k2 in there, and then look at their bracket, right? That's going to be some other element in our Lie algebra, and then just look at their span, and that's going to give you some other subspace. Okay? And one of the reasons why we do this is because it's actually notationally convenient to just to write it this way, and because what we really want to do is just look at the span of all the commutators and say something about them, or say something about the commutators. A specific case of this is something called the derived algebra of L, which is the subspace L bracket with L. So that's just going to be the span of all the commutators sitting inside of L. And this thing is kind of similar to the commutator subgroup if we continue that group theory analogy. And understanding this is one of the key things, as we'll see, and understanding how L bracket L, the derived algebra works, and in particular the quotient of L bracket L in L, which we'll define momentarily. How that works will be pretty important as well. And so let's take a look at some extreme cases. We'll be talking about this later on, so I won't go too much into it here, but some extreme cases, right, is when L bracket L is as small as possible. So if L bracket L is equal to 0, then that tells you that the span of all the commutators in L is just 0. And so, in particular, any individual commutator is 0. And so this tells you that L is abelian. And it goes the other way. If L is abelian, then all the commutators are 0. And so we get the reverse arrow. So that's one case. The other extreme is if L bracket L is actually equal to L itself. And now this doesn't, there's no really if and only if here. Well, you could concoct one, but an example of this would be SL NC, where n is some natural number, let's say greater than 2. And so recall that a basis for this guy, right? This guy is the span of the EIJ, where 1 less than or equal to I, not equal to J, less than or equal to N, and then you have the EI I minus EI plus 1 I plus 1, where 1 less than or equal to I, less than or equal to N minus 1, right? And so what it turns out is that, and you can easily verify this, is that if you just look at the basis vectors themselves and you just bracket them together, you can actually just reproduce your basis again. And so what that tells you is that all of your basis vectors sit inside of the derived algebra. And so that means just by extending by linearity, the derived algebra is L. And so this is actually an interesting condition, because this is a necessary condition for your Lie algebra to be semi-simple, which we'll again talk about later. All right, so with that being said, let's actually define what an ideal is. Definition. an ideal I of a Lie algebra L is the subspace of L such that if X is an element of L and Y is an element of the ideal, then X bracket Y also lies in the ideal. So let's draw a picture to represent this. We have L here, and we have I sitting inside here. And what this condition is saying is that if you give me some Y inside the ideal, and you give me some X anywhere inside L, it could be inside the ideal, it could be outside the ideal, then the vector X bracket Y also sits inside the ideal. So this is much stronger than the subalgebra condition. The subalgebra simply said if you took both things inside the subalgebra, it sits inside the subalgebra. So what this tells us is that immediately ideals are subalgebras. They're stronger than that. They're just absorbing everything outside as well. So with that being said, I hope that's clear. Let's take a look at some examples. And so the first example is just the zero subspace, right? If your only vector is 0 and you bracket with stuff outside of the ideal, so the ideal is 0 and it's sitting inside some Lie algebra, and you bracket with stuff outside of your ideal, which is just 0, you're going to get 0 again, no matter what you bracket with. And so that tells us that the zero subspace is an ideal. At the other extreme is L itself. If you bracket two things in L, it's going to end up back in L. And so these first two examples are kind of the trivial ideals that if I don't say otherwise, it'll probably, if I say ideal, we're probably not talking about these because we generally want to make statements about non-zero proper ideals. And so the next example, which is less trivial, is the center of your Lie algebra. And so what the center, recall, is that it's everything in L that commutes with everything in L. Okay, and so the ideal, the center is an even stronger condition than the ideal condition, because it's saying, not only is it saying that it has to lie inside of your center, it's saying it has to actually equal 0. So here, right, this guy is actually going to equal 0, and of course 0 is going to be in your center, and so the ideal is even stronger than the regular, or excuse me, the center is stronger than the ideal condition. So this is an ideal. And then the last thing here we just talked about is the derived algebra. The derived algebra is an ideal of L. Now, as we saw earlier, it may not necessarily be a proper ideal. It could be 0 or L, but it is still an ideal under this definition because it's the span of all the commutators by definition. If you're a commutator, you sit inside of L bracket L, and so this guy is an ideal. And so just some remarks here. First of all, note that if L is equal to the center, if L is equal to Z of L, then L is abelian, right? If and only if. Yeah, that's good for now. Yeah, okay. And actually, let me give a concrete example. So a concrete example of an ideal, right, is if, let's say, L is equal to GL n comma C, then an ideal of GL n comma C is actually equal to SL n comma C, n greater than 1. And then another example is if L is equal to the triangular matrices, then the strictly upper triangular matrices is going to be an ideal. In fact, I'm kind of cheating here because I know a priori that these are actually just the derived algebras, right? And so this is actually very important to verify as well. So you should verify this. Verify that the special linear algebra is the derived algebra of the general linear algebra, and verify that the strictly upper triangle matrices are the derived algebra. They form the derived algebra of the triangular matrix, of the upper triangular matrices. Okay, and so now we can talk about some simple things that we'll use later on. if I and j are ideals of L, then the following are also ideals of L. So first of all, there's I plus j as just a vector subspace. That's also going to be an ideal. I mean, if you take some arbitrary x inside of L, and then you bracket it with some arbitrary I plus j sitting in here, just use linearity. This is x bracket I plus x bracket j. And so this guy sits in I, this guy sits in j, so this entire thing sits in I plus j. Now here, right, I bracket j, right, this is going to be the span of all the commutators of something in I with something in j. So an arbitrary element is going to be a span of some I bracket with some j, but let's just look at x bracket for some x in L with I bracket j. So just to be extra clear here, an arbitrary element of I bracket j does not look like this. It's the span of things that look like this. Anyways, with that being said, we can apply the Jacobi identity here to simplify this thing. So this is equal to minus I bracket j with x minus j bracket x with I. So I'm going to write Jacobi. Now, of course, j bracket x is going to lie in j because j is an ideal, and similarly here, x bracket I is going to lie in I. So we call this I prime, and so this is going to be an element of I bracket j. Okay, I hope that's pretty clear. And so implicitly here, right, even though this says j bracket x, it's not of the form x bracket j, it doesn't matter. That's one of the nice things about ideals in Lie algebras, is that really they're all two-sided because of the fact for anything in our Lie algebra, x bracket y is equal to minus y bracket x. So it doesn't matter if we bracket on the right or if we bracket on the left. And so that simplifies a lot of things, especially if you've done things like in abstract algebra and you've focused on like left-sided ideals or right-sided ideals or two-sided ideals. It just makes things nice, so we don't have to worry about the side on which we bracket. All right. Okay, so the next notion we're going to talk about is something called simplicity. So any non-abelian Lie algebra L is said to be simple if it contains no ideals except 0 and L. So right off the bat, just an important remark is that we say non-abelian just to exclude the one-dimensional Lie algebra L. Because if L is the one-dimensional Lie algebra, then technically it's simple, right? It has no ideals except 0 and L. But it turns out later on in the theory of semi-simple Lie algebras, which, as the name might suggest, is related to simple Lie algebras, we don't really want the one-dimensional Lie algebra sitting in there. So we exclude that. And so let's take a look at example of a semi-simple of a simple Lie algebra. Excuse me. So let's say L is equal to SL to C. Okay. Then recall our commutation relations and recall the things that span SL to C. So we have H. So this is, let me rewrite it for good measure. This is equal to the span of E, F, and H, right? Where E is equal to 0, 1, 0, 0. H is equal to 1, 0, 0, minus 1. And F is equal to 0, 0, 1, 0. And recall the commutation relations, which are H bracket E is equal to 2E, H bracket F is equal to minus 2F, and E bracket F is equal to H. So immediately, what we're trying to show that there are no ideals, right? So the goal is to show that L is simple. And so immediately, suppose E were inside of your night. So let's say we have an ideal, right? And it's non-zero. So suppose E were sitting inside of the ideal. Well, then I could just bracket E with F to get H, right? And because I could bracket with things outside of the ideal and to say that the result is inside the ideal. So I know that H is inside of I. So I have E and H inside of I. Well, then I have H inside of I. I could just bracket that with F. And then I'd have F inside of I. And so I have E, F, and H all inside of my ideal. It's an ideal. Obviously it's an ideal. It's going to be my SL2C. The same thing applies to F, the same argument. And if H is inside of I to start with, let's say it's just a span of H, or it contains H, then I could just bracket H with E to get 2E. So I know E is inside. And then I could bracket H with F to get minus 2F. So I know F is inside. And so I have, again, SL2C. And so the whole point is that if any one of these guys, E, H, or F, are sitting inside of my ideal, then it has to be SL2C. So let's say we had some arbitrary C0E plus C1F plus C2H. Okay, so at the moment, right, I'm not saying E, F, or H sit inside my ideal. I'm just saying some linear combination of them sits inside. Okay, so this is the most general case. Let's bracket this guy twice with E. Okay, if I bracket twice with E, so I'm going to bracket once with E, and that's going to make this E vanish. It's going to, and when I say bracket with E, I'm going to bracket on the right. So this thing here is going to become minus C1H, and then this guy is going to become plus 2C2E when I bracket on the right with E. So I'm going to do like that. Okay, and then I'm going to bracket on the right with E again. This guy is going to vanish, this guy here. And then this guy, because I'm bracketing on the right with E, is going to become minus 2C1E. Okay? And similarly, if I bracket on the right with F twice, I'm going to end up with, let's see, minus 2C0F. Okay? And so what that's telling you is minus 2C1E lies inside of the ideal, and minus 2C0F lies inside of the ideal. So if C1 is not 0, we're done. Because if minus 2C1E is in the ideal, then E is in the ideal and we're done. And the same thing applies to C0. If C0 is not 0, then F is in the ideal. And then everything else is in the ideal. So the only case left is that if C1 and C0 are both 0, if this is 0, if 0, and this 0, then that term vanishes, and we just have C2H left. Well, C2 can't be 0. I mean, the implicit assumption was that this vector was non-zero. So C2H is going to be in the ideal, and so H is in the ideal by linearity, and then by the argument at the start, E and F are in the ideal. So no matter what vector lies, if you have an ideal, then that's not 0. Then E, F, and H, the basis vectors of SL2C, also lie inside. So this is an example of a simple Lie algebra. And the reason I spent so much time on this is because this is one of the most important simple Lie algebras. Just some remarks, right? If L is simple, right? If L is simple, let me change colors here actually. If L is simple, let's go to blue. So if L is simple, right, recall the center is an ideal. So that means the center has to equal 0 because it's also non-abelian, so it can't equal itself. And in particular, recall the derived algebra as an ideal. So that means L, bracket L, is equal to L. So these two things hold. Of course, the converse does not imply simplicity. Okay, so let's go on to the next thing here, which is the notion of a quotient algebra. Okay, so the quotient algebra, so let I be an ideal of a Lie algebra L. In most cases, we just consider a non-zero proper ideal. Then the quotient algebra L mod I, or L quotient I, is the quotient space. L mod I is a vector space, so you should have studied this in linear algebra, endowed with a Lie bracket defined as follows. if you have some x plus I, an element in L mod I, and y plus I, an element in L mod I, then I'm just going to define the bracket of those two elements to just inherit the bracket from I. Okay? And so I recommend you look up, if you've never seen the quotient construction before, I recommend just looking it up, or I might post a link in the description. And the reason is it's a pretty straightforward thing, so I think you could just pick it up on your own if you haven't seen it. And you should have seen it in linear algebra. And so what really matters to make sure is that this bracket is well defined, right? Because like, remember that x plus I is equal to x prime plus I, right? If and only if, like as elements in your quotient space, x minus x prime is an element of I, right? And so so recall that the whole idea is that when we quotient out your ideals, you're making things equivalent up to something inside of your ideal. So you're saying is, okay, x differs from x prime by something in the ideal, so we'll just say they're equal up to something in the ideal. That's the whole idea. Just like think of modulo with integers, right? 8 and 3 are equivalent mod 5. Because you add enough 5s, you get from 3 to 8. Okay, so that's the same idea here. So x and x prime are equal if x minus x prime is an element of an I, right? So what about this whole bracket business? Like, how do you know that that works? And so this is where the ideal condition is very important, right? So if I had different representatives, x prime plus I, bracket with y prime plus I, and these guys, x prime represents the same thing as x, and y prime represents the same thing as y, then that means this is equal to x plus some vector u sitting inside of I, bracket with y plus some vector v sitting inside of I. Now we're going to use linearity, and so this is equal to, by definition, x plus u, bracket y plus v, plus I. And then use bilinearity here. And so this becomes x bracket y plus x bracket v plus u bracket, u, okay, I cannot draw u bracket y plus u bracket v, okay? Plus I. Now here's the key thing, observation. V is inside the ideal, and because it's an ideal, this thing lies in the ideal. U is inside the ideal, so this thing, by the ideal property, lies in the ideal. U and V are both in the ideal, so this lies in the ideal. So this entire sum end is in the ideal. So this is actually, we can suppress that into I, and we can say this is x bracket y plus I. And so our choice of subspace representative did not matter. Coset representative. So so this is the quotient construction, and that'll be pretty important as we go on. Okay, so now two last definitions. First of all, we have the normalizer or idealizer of a subspace K in L is NL of K is equal to X element in L, such that, so this notation here is interesting. All we're saying is that you take X bracket with K, and then you take the span of that, okay? And so we're saying that sits inside of K. And if K is equal to its normalizer, then it is self-normalizing. So just some remarks here. First of all, the reason we say idealizer is that in the case K is a subalgebra, then the NL of K K sits inside of NL of K, and K will be an ideal inside of NL of K. So it's the thing that makes, it's the smallest thing that makes K look like an ideal. Or, excuse me, it is the largest thing that makes K look like an ideal. And self-normalizing is a really important property when we talk about something called the Cartan subalgebra. We'll talk about that later. The Cartan subalgebra is self-normalizing, and that'll be really important later on. An example of self-normalizing matrices are going to be the diagonal matrices. The diagonal matrices sitting inside of GLN comma C. These are self-normalizing, and also the triangular matrices are going to be self-normalizing. Okay, and you can verify these. I think this is an exercise in the book actually. And then the last thing, right, is the centralizer of a subset. And so this is the same thing, except rather than so like what in the case of the normalizer, right, what it's doing is that it's sending it back into K. In the case of the centralizer, we're actually going to send it to 0. That's the whole idea. And so the centralizer is basically this largest thing in which S sits inside of, so that S is central. That's the whole idea. So the CL of L itself is going to be the center of L. Okay, I hope that makes sense. So these are just some simple definitions, and there are numerous problems you can work out, and as we need properties about these things, we'll talk about them later on. And so that will conclude this video on ideals. We'll move on to homomorphisms and representations and how those connect to ideals in the next video.